ではセッションに入りたいと思います。次のセッションは、コンラッド・マラウスキーさんで Zen of Akka です。
Okay, thank you. Yeah, let's jump right in. There's lots of slides, but I think we'll be able to go through most of them. So my name is Konrad Malawski. I work on the Akka team at TypeSafe. I also did the reactive streams, and yeah, Akka HTTP, I'm maintaining it currently. So other things I did, I run the Geekon conference in Poland, and I'm part of the program committee at Java 1, so various community things in Poland and in the US. Okay, so where is Akka used? Akka is used as various organizations, such as these. Many logos you probably know. And the short question to you guys, so who's actually using Akka? Okay, so some users, very nice, thank you. So this talk is basically a collection of tips and a way of thinking when writing programs using Akka, which is why I thought the state of the mind while writing Akka applications was the appropriate title. We'll see how far we get. So another reason why such title is the Tower of Programming book. Maybe you know it. It's a funny book which takes the Tao philosophy and in a funny way applies it to programming. So a Zen master explains, a Tao master explains how to program, and it's a bit interesting if you give it a read. But then there's another one, the Zen of Programming. Again, a Zen master explaining the Zen of Programming. So here I am trying to explain the Zen of Akka. So, the Akka landscape. So for those of you not familiar with Akka, what is it actually about? It's about these modules. So that's not all of them, but that's the most interesting ones. The core of it, of course, being Akka actor and a cluster, and then the more specific ones like persistence and HTTP. Okay, so first, Ichiban, yes. One actor is no actor. So actors are not really meant to live in isolation. They are really lonely, and they can do only three things. They can reply to messages, they can drop a message, or they can send a message to itself. By itself, that's not much. But it gets interesting once the actor gets a friend and can communicate with it. Because then, if I don't know how to handle a message, I can ask Specialist Bob, and Specialist Bob maybe has workers, and the workers can do the job better than Bob can. And this is where different patterns start to appear. So here we have a worker pool, right? A different set of actors doing the same thing. And then we can have also direct replies. So even though this message went through this route, the reply is direct to whoever asked the question. So they are meant to work together, and yeah, child actors are usually short-lived, right? They do a very specific task and then they go away. Okay, so what do we do with actors? So some applications look like this. It's this whole mess of actors and you don't really know what's happening. Here by colors I mean different classes of actors. Right? There could be a blue one for fetching some metadata, some pink ones for doing some blocking operations, etc. But if it's not structured, it's really hard to tell what's actually going on. Here, however, when we introduce a parent-child relationship between actors, then you look at it, you know where the entry point is. The entry point seems to be all the blue actors or the black ones, and the black ones don't really communicate with someone else. And this already helps with structuring the application. You start to think about it as in tiers and who talks with who. And translating that to code, of course, that's who starts which actor, right? Okay, naming. Default naming. So if you just start an actor like this, you say context actor of child props, the default names will be $A, $B, $C, so that's not very descriptive, right? So why are the names like that? Well, for one thing, it's very cheap to generate, very fast to generate. We use a function called base64 from an incrementing sequence number, right? That's why we get A and B and C, etc. But it's not very helpful when you're trying to debug something and actor A threw an exception. What is helpful, however, is, well, at least if they are called like this, you have a fetch worker 1, fetch worker 2. If all of them do the same thing, and they have a similar name, then at least you can, more or less know what the actor was doing. If you need to implement such a thing, it's just a few lines. You can have a sequential actor name, and then you just call next, and you get a next actor name. The code will be online, so you can read it afterwards. But that's not the best thing we can do. The best thing we can do is have proper names. So if an actor is downloading movies from some sites like YouTube or Dailymotion or Vimeo or Nico Nico, then you can have it in the name that it's a fetch actor from YouTube, and that's the identifier of the movie it's been downloading. So why is that important? For one thing, if you look at your actors, you know which movies are currently being downloaded, just from the structure. But also, if it fails, then the parent actor, in its supervision strategy, will get, the reason the child actor failed, and the sender of that message will be that child actor, right? So here you can figure out, which movie did we fail downloading, right? And you can, have better logging then. And as we all know, understanding what an application does is really the part about building applications that need to survive production. Small side note. So you can write the same thing, effectively the same thing in small different, with a small difference. So you can say with string interpolation, so S and generate ID, or you can do the same thing with these brackets here and then write the generate ID here, right? The difference is that, here we don't build the string unless debugging is enabled, right? So perhaps we're saving some string concatenations, which surprisingly can be really heavy for GC sometimes, if it's a really heavy logging actor. Okay. Number 4, the matrix of mutability. So here we have, we have values and variables in Scala, and also we have immutable and mutable collections, right? So how should one go about, which one should I pick? Well, of course, having a value which is immutable is the easiest and both nicest thing, right? If it's a fact and it will never change, right? Immutable collection in a value, it's a fact. Then having an immutable collection in a variable field is already okay. I mean, it's not the nicest thing, but it's okay. Why is it okay? And better than the mutable in a var, right? So it's actually better because if I give the value that I observed to someone else, he or she cannot change it. Whereas if I accidentally give someone a mutable collection, they could start mutating the mutable collection, right? But here, if I leak the immutable collection, I'm still fine. So it's good for messaging. You can just put whatever state you have into the message and send it over. And then there's the last one on the matrix. So mutable variables, just please don't. It's the worst thing, and there's basically no reason to do that any time. So anyone could mutate it, and it could change all the time, and at any time, the reference, so just don't. Encoded translates to either the val, right? It's a val, or it's a mutable, for example, a list buffer, right? Very easy to spot. So if you spot this, just figure out which one of these you should choose, and choose one of these. Don't keep this in the code base. Okay, go on. So blocking needs careful management. So what do I mean by blocking? So blocking is the situation where someone is doing something very slow, for example, reading from the database, but it's not giving up the thread, so it's still using it. And for example, if we had just one CPU and we have 2 actors, then the second one wouldn't be able to do anything because we just wasted the entire processor, thread in our land, since we're on the JVM. Okay, so in blocking is bad because instead of doing something else, we're just wasting everybody's time. Funny example from Stack Overflow, the question was, blocking in a future blocks the server. For me, this is a tautology. That because I mean you can read it as blocking causes blocking. Yes, blocking causes blocking. However, I don't mean to laugh at the question. It's a really valid question, right? So someone wanted to simulate what if inside of a root I would be doing something really heavy, right? Something that takes a lot of time, effectively blocking, right? So the question is valid. How would we avoid this grinding the server to a halt? So before we dive into, let's see what actually happens to the application when we do such a sleep in the middle of the code. So here we have an Akka HTTP root, right? And here it's a future, and in the future we sleep, right? 5 seconds of sleeping for every incoming request. So you can easily imagine that builds up and suddenly the entire application is sleeping, which is exactly what happens here. So we have a number of threads on the dispatcher, and they're all sleeping basically, right? And yeah, after they are done sleeping, we are waiting because there's nothing to do. This is where the idle timeout triggers actually. And where's the application doing anything? Well, here. In case you don't see where the application is doing anything. Okay? It's not doing much. But I would prefer the application to do much. So, how can we solve it? So the Akka way of solving these things is to configure a blocking dispatcher. So it's backed by a thread pool. So that's a set number of threads that we pre-allocate. In this case, 16. You have the details on configuration you can read on in the docs or later. And then we have 16 threads pre-allocated for the sleeping. And we use it like this: system dispatchers lookup. And by name we get it, my blocking dispatcher. And then, when I sleep here, it will be sleeping on the my blocking dispatcher, right? So the default dispatcher is not impacted by the stupid sleeping. So always do this when you have any kind of blocking operations, because then the rest of the application can be responsive. Okay. So we have this never block mantra, and it sounds cool, but it's not very helpful. The actual meaning behind it is when you really have to block. Well, first thing, avoid blocking. Second thing, when you really have to block, isolate the blocking. Okay? Okay. So, what about await? There's this await word in Scala. What can we do instead? So sometimes when people first write code using futures, they write compute things. It gives me a future things. So I await on the result of the things for at most 3 seconds. But well, that's again blocking, right? We blocked the thread we just are listening on here. And then we await again, get the details, and we await, and we await. So that's very bad. Instead, we can use the for comprehension, right? So here we say, we'll compute the things, and when you're done, more details for the things, and when you're done, just return the things with the details. And this is still a future. So when the future completes, we will do something with it. So this is non-blocking. Right? However, it's not semantically quite the same, because above here we had a timeout, right? It's awaiting at most 3 seconds. Here we are not speaking about timeouts. So in order to kind of mix in a timeout, we can have a future that will fail after 3 seconds. And this is something we can do using the Akka pattern after. So it works like this. After 3 seconds, do this thing. So after 3 seconds, we have a timeout exception. And then when we want to collect the values, we just say future first completed of, either it's going to be the things, or it's going to be the timeout future. So of course, if the things come faster than 3 seconds, then we get them, otherwise it's the failure. Okay, so another way to get around without blocking. Okay, so Java serialization. That's a turtle, in case you didn't know this. So what does that mean? That means that Java serialization isn't the fastest animal on the planet. And yeah, it is the default one. So if you use Akka, you're probably using the Java serialization. The reason is a bit historical. We used to have it for a long time, and it's also very easy to get started with it. It doesn't need any pre-configuration or any work to make a normal Java object serializable using it. Better ones would be, for example, protobuf or cryo, but they require additional work. So here's how you can fix the slowness problem. So why is the slowness actually happening? So you have this ping pong case. Two actors are sending each other a message, or a ping pong ball, and on a local machine it's really fast. The table is really small. But once you go distributed, you have increased latency because with serialization involved. And sadly, with Java serialization it looks like this. So the table is really big, so it takes a lot of time to cross it. But since Akka 2.4, we are actually logging a warning whenever you do that. So at least now you know that you're doing something wrong. In previous versions, well, we knew that it's wrong and we were telling people that it's wrong, but if you didn't read the mailing list, then maybe you didn't know. So now you'll notice in the logs at least. So, let's do a short benchmark, how really bad it is. So here's a very short benchmark, and I'm measuring a ping pong case. And it's still on a local machine actually. But you can see the Java serialization is 25 microseconds per one message sent. And with it off, we're below a microsecond. Right? So that's really intense overhead. So, a quick solution that you may consider, but please check out other serialization frameworks before you dive in. Here's a list of them. You can use, for example, cryo. Cryo is nice because it doesn't require that much manual labor for it to work. So you just configure it like this. You say, yeah, cryo is a serializer, and my company example should be serialized using cryo. And performance-wise, it's alright. Right? Here we're doing 4 micros per operation. And so why is it actually so slow? Well, for a number of reasons. For one reason, it's just slow, but for another reason, it's really big. So this is how much Java serialization of an empty case class. This case class, if it's empty, this is how much space it takes in Java serialization. This is how much it takes in XML. Right? So XML is more to us than Java serialization. Think about it. In JSON it would be something like that, and in cryo it's serialized basically as the default values of the fields. So basically nothing. Okay, so and also, if you have any kind of persistence system where you store the messages, you really should invest in a proper serialization strategy. I didn't cover this here, but there's really, really good docs we wrote in the Akka documentation about doing that. So think about it, because there it's also about evolving your domain through a number of years of persistence. Right? So don't trust me. Basically, trust no one and benchmark everything. And whenever you see a benchmark, don't trust it. Just do a benchmark yourself. Here's a number of good tools, JMH or the SBT JMH plugin. Or on Linux, the best thing you can do is perf events or a good profiler. So Visa 2 I really like, but any good profiler will do. So benchmark yourself. So, number 8. Let it crash. So, we have these two words that sound similar but are not. So, we have errors and we have failures. And this distinction has been made in the Reactive Manifesto, co-authored by Jonas, who's been talking here at this conference as well. But let's go into an example. So I have a vending machine, I insert some money into it, and actually, well, it's not enough money. I inserted 50 yen, and the drink was costing 120 or something. So that's actually an error. So on the inside, there's some actor hierarchy. We are doing something with the money, calculating something. And this guy is supervising this, well, vending machine actor, let's put it this way. And these actors are responsible for the rows, for example. I'm just making up an example here. Probably won't be like that in the real system. But the point is that this guy validates that it isn't enough money and responds with an error. The error is not enough cash. And this is different than row 3 is broken, which would be a failure. Right? So there is enough cash, but I can't give you your drink because something is broken. So the difference is in the person who is interested in this information. So the failure is interesting to whoever is maintaining the vending machine, right? I want to send out a guy to fix the vending machine, right? But for me as the user who inserted the money, well, maybe I care, maybe I don't, but for me it's just an error about, well, sorry, you can't have your drink, right? So there's a difference between failures, so something blew up, something doesn't work as expected, and an error, which means, well, we can't do something, sorry. So that was supervision, but we also have backoff supervision. So backoff supervision means when we give someone more time to come back. So the goal is to let things crash, but also let them recover gracefully. So when we have a persistent actor and it needs a database, but the database blows up, then, well, the actor will eventually get a persistence error, right? Because, well, sorry, we couldn't persist your message. The problem is, so we don't do that in Akka. We did this previously, in previous versions, before it went stable. It could happen that the database is still down, but we are recovering, right? So the actor blows up, recovers, blows up, recovers, blows up, recovers, and suddenly we are killing the database, thanks to all the recovering. So you can imagine in a system like that, you have some database cluster and you have some application cluster, and suddenly all actors in your application would be hammering the database to recover. So that's a bad thing, right? Instead, what we want to do is give the database, or any kind of resource actually, some breathing space to recover. So how do we define this breathing space? So instead of restarting right away, we stop, and then there's a third party, or a backoff supervisor, that will determine on the backoff timer when it's time to restart. So this backoff means that at first I will restart after 3 seconds. If it still blows up, I will restart after maybe 12 seconds. It still blows up, so I will wait maybe 30 seconds, and so on. Right? This guy is pretty configurable, so you can configure how it does the restarts. But the point is, it gives breathing space for whoever was under load to come back online. Okay. So that's a quick one. If you have an actor that looks like this, maybe even worse, maybe there's 20 messages or 30 messages, maybe there's something fishy going on. Well, this fishiness you may recognize. This doesn't happen in Akka. But why doesn't it happen in Akka? Because we don't need callbacks, right? Because there's one callback, the receive method, right? You get a message and you reply with a message. But when I see a very long receive, it feels a little bit like the pyramid of doom in maybe JavaScript. The problem here is, well, this works and it's fine, but let's look into it a bit more in depth. By looking at the messages, we maybe can see that, aha, so this was actually awaiting instructions, and when we get a make something message, we become making things, and then we make things, and once we get a do other things message, then we go back to awaiting instructions. So it's actually not a one very big receive method, it's a number of states that the actor goes through. And they are smaller and therefore more understandable, right? Maybe you can even test them separately or make them different actors, maybe. So we also have a TSL, which helps you with that. You may or may not like its style, it's a personal preference thing, but they are semantically equivalent, and the core is about having these states and transitions between them. Okay, cluster convergence, and this is slowly one of the last topics. We're pretty good on time, I think. So, cluster convergence and joining. So, convergence is this situation in the cluster Actually, one short question. Who in the room has used Akka cluster? Okay, a few people. From those people, do you know what cluster convergence is? Right. So this is why I'm doing this talk, because people don't realize. So this is a very important thing, but it is in the docs, but maybe it's not as very big and red as it should be. So we'll see about improving that. So the only point in time where we do joining and leaving decisions in the cluster is when we have convergence. So convergence is, here's the definition, when a node can prove that the state it sees has been observed by all other nodes. Basically, it means that everybody agrees on the state of the cluster. Okay. So here's a diagram. You may have seen it in the docs. And essentially, it means that there's a state called joining, and then it goes to up. So you're joining a party, you're saying hello, hello, and then you're up, you're ready to party, and everybody said hello, right? And the opposite way, it's the same. You're leaving, so you're saying goodbye to everyone, and once everybody has seen your goodbye, then you're exiting, and then you're out, right? You're out the door. Which I'll talk about in a second. This is a modification in our protocol called weekly up, and I'll explain in a second what it is. But remember that it's between joining and up, right? You'll see in a second what it is about. So let's say we have a cluster party. We have two seed nodes. So a seed node is like a host of the party, right? You know, well, Takeo-san is doing a party, I'm going to his place, right? So you know the address of the seed nodes. And here, Kurt is going to the seed node and joining the party. So, like I said, everybody in the cluster has to know that someone else arrived. So seed node 2 tells seed node 1 that Kurt wants to join. So here I mark that who knows about Kurt. Okay, Kurt knows about Kurt, sure. This one knows about Kurt. And now the third node will also know about Kurt, right? Because it got told by seed 2. So once we have it, then the guy with the funny hat, this is the cluster leader. So this role can move around. So if seed node 1 dies, seed 2 would become the leader. There's always one leader. So leader decides that, okay, everybody has seen Kurt, I'm moving him to up. So basically you invite him to the party. So now he's in the cluster. Everybody has seen Kurt and he's ready to party on. So another situation is when someone in the cluster is unreachable. So unreachable would mean, well, you went out the door without saying goodbye to anyone. So no one really knows where you went or if you're coming back or not. So we call this unreachable. I can't phone you up, I can't reach you. So now the problem is, Ray wants to join. Same situation, right? Ray wants to join, tells the seed node, but, well, he can't really join because we cannot prove that everybody knows about Ray, because Kurt is, we can't reach him. We can't tell Kurt about Ray, because he's unreachable. So this is where the new state comes into play. So the reason we have this very strict thing is for consistency. So if you really value consistency, then keep this setting off, and that's the default, because then eventually either Kurt will be ejected from the party, or Kurt will come back, and then everybody is fine. But maybe if you need a really quickly scaling up scenario, so you're adding nodes to a cluster that is, almost failing because of load, and you want to add more nodes, you actually do want to accept the new guy, even though not everybody yet knows about the new guy. So this is called this allow weekly up members. So here the leader decides, well, Kurt doesn't know about Ray, but, let's invite him to the party anyway, because we need more people, for example. And then, once Kurt comes back, or if he's ejected from the cluster, then everybody knows about this new node, and then we move it from weekly to up. So what's the difference actually? Well, the difference is for you can listen on these events, and where some of the cluster tools automatically would migrate data. Right? That's the only difference here. Okay. So that's the joining part. But what's the leaving part actually? So leaving, let's say it's your birthday, well, Bill's birthday, Joby party, no? Okay, and he's going home. So he's going home, it's not his place, he's going home, but no one heard him say that. So, you know that sometimes, it's a really heavy party, he says, oh, I'm going home, and he disappears. That's a bit scary. Well, usually they wouldn't hear him because either the volume was too loud, or in our very Akka-specific situation, it means you say cluster leave self, and then you say system exit, right? Line after line. What happens then is, well, the cluster will be about to tell everyone that it's leaving, but you killed the JVM. So there wasn't enough time to tell everyone that you're leaving. So it's almost as if you disappeared. Right? So don't do that. When you're leaving, you should say cluster leave, and then if you get an event that node down self, then you shut down the JVM. Okay? So after everyone knows that you're leaving, not sooner. Okay, so what happens here is the failure detector kicks in. So failure detector is after how much time will I start worrying where Bill is, right? Should I start worrying right away, or after half an hour, etc., etc. And this is on the diagram, the dotted lines. So you can become unreachable from any of the states, basically, right? And it's the other nodes that decide, well, I can't reach him, he's unreachable. But the decision to go from unreachable to down has to be explicit. So we either have a auto-downing feature, and it's not really safe, I wouldn't recommend it, so don't turn it on in production. It's good for demos, but not for production. Or we have a split brain resolver, that's a commercial feature, but it really does the job right. So the other nodes decide, well, so is he down or not, and they communicate with each other. Okay? So when you're down, so let's say the party guys decided, okay, Bill is down, Bill's not coming back. Right? When you say someone is down, he's not coming back. But what if he comes back? Right? Maybe Bill was just at the parking lot, or maybe grabbing more beer or something, and he comes back. Or in Akka terms, a network partition healed. Right? There was a network partition, and now it's okay. So it can communicate again. So communication resumes, but Bill was already declared down, so he's been ejected from his own birthday party. So what happens then is, machine label. Yeah, because once a node is declared down, oh yeah, for the English speakers, you are already dead. Yeah. Once a node has been declared down, we will never allow it to rejoin the cluster. Why do we do that? Because declaring a node down is different than unreachable, right? It was a conscious decision, or automatic one by one of the big strategies. And the reason we do it is to preserve consistency in the cluster. So if the party is doing something and decided, well, let's go home in 5 minutes. Everybody on the party decided that. But Bill went to the store and bought 50 liters of some alcohol and decided it's a great idea to drink 50 liters more. And he comes back to the party and says, well, let's drink 50 liters of something. Well, he may have decided this on him by himself, but you probably don't want to trust him anymore, right? In Akka terms, this would translate to a node calculating something on local data, but the local data perhaps is out of date, right? Because it couldn't communicate with the other nodes, so you cannot trust it anymore. So this is why we do that. On a side note, we mostly need this kind of behavior when we do single writer things. So Akka persistence or any kind of file access, something like that. That's accessing something with a single point of decision making, right? But whenever you use some kind of system that doesn't have a single point of decision making, for example, Akka distributed data, that's CRDT based, that's convergent data structures, it works like that everybody gives a vote, right? And everybody will come to the same agreement by the end of the day. Even if he comes back with a very bad idea, you would, overvote him because you're going home, so everybody is going home. So that's where CRDTs and distributed data is useful. Important thing, what we did not talk about, we did not use the word quarantined. And when talking about the Akka cluster, the word quarantined doesn't actually appear at all. It's not a cluster thing. It's a remoting thing, and yes, remoting uses that, and cluster uses remoting. But if you're using cluster, you talk about down and unreachable, not about quarantine. Sometimes people are confused and say, well, something was quarantined and then downed, or the other way. That's slightly mixing things up. So usually you should talk about unreachability. Okay, so that's the last bit. So if a phishing tool, if a phishing rod is a tool, Akka is a toolkit. So Akka is a toolkit and not a framework. So sometimes we get questions, why doesn't Akka do this for me? Well, sometimes maybe it's nice to have it built into Akka, but it's a toolkit and you can build things from it. So this is something we really try to do with Akka, is to have a minimal set of really, really good pieces you can build upon and not just throw everything in. Okay, so also the less powerful abstraction can be built on a more powerful abstraction. By that I mean, if we have Akka actors, they are a very powerful abstraction, and all of the, futures are not built on Akka, right? But streams and Akka types are built on Akka, right? So these are more constrained, but these are more powerful. So you need to pick which you need. And also, these two are local abstractions, so future and streams are in the same JVM. And the distributed systems things are actors. Here's a quick information about how they differ. So futures are only for a single value, right? It's a future of one thing. A stream is, it can be multiple things, but it's a static layout. Right? It cannot really change. It's like a pipeline, you put it there, and it stays the same. But actors, both Akka typed and Akka actors, can be very, very dynamic, right? So they are less constrained, they can do anything basically. But again, that makes them a bit more complex than the Akka stream solution, for example, which is static and you can look at it and that's the thing. So Akka is a toolkit, not a framework. And for example, we had a customer who really wanted to use Akka persistence, but it didn't fit the use case at all. But they still used it, and then they said it's crap. Yes, because you used it and it didn't fit the use case, right? So in my opinion, it's way better for everyone if you know your use case, and if you're mature enough to say, well, this doesn't fit our use case, then taking it and applying it to something that doesn't match. However, on the other hand, if you find a problem that really fits Akka, either actors or streams or distributed data over cluster, then everything just falls into place and works really well. Right? So you need to pick the right tool for the right problem. This is my last and most important message from the talk, I think. Okay, last but not least, we have a great community. And this is how you can join us and help us out. Yeah, we are mostly English speaking, but in writing I think that's going to be doable. We have a, of course, website and everything is on GitHub, but we also have a chat. Okay. We have a chat, Akka and Akka Dev, so if you want to join and talk about it, we are more than happy to. A bunch of links. Here's our commercial solution, so a bunch of them I hinted at, but first loads of more stuff, and I do think you should have a look. So that's all I had, and last quote of the day: after 3 days without programming, life becomes meaningless. From the Zen book. I thought it's arigatou gozaimasu.